Good morning, everyone. My name is Vittoria Laghi, and I'm a postdoctoral fellow in structural design at University of Bologna, Italy. Today, I will present you the experimental investigations of wire-and-arc additive manufacturing stainless steel rods. The application of metal additive manufacturing in construction has started a decade ago. The first explorations were limited to small connectors realized with powder-based printing techniques for high architectural appealing structures. From 2017 on, a technology has been developed to scale up the printed parts up to serialization to a real-scale footbridge entirely realized in 3D printed steel. This technology is referred to as wire-and-arc additive manufacturing, acronym WAM, a well-based additive manufacturing technology which makes use of off-the-shelf welding equipment mounted on top of large robotic arms, able to print pieces several orders of magnitude bigger than the printer itself, up to several meters span and few meters high. The techniques have been developed. Two of them, the so-called continuous printing, a layer-by-layer deposition to realize continuous shell-like elements, and the so-called dot-by-dot printing, in which drops of metal parts are printed one on the other to realize rods and lattice-like elements. The main advantage of this technology are the fast production of large parts with ideally no geometrical constraints in shape and size and high structural resistance. On the other hand, there are several open issues to investigate: the lack of material characterization, the lack of mechanical and geometrical characterization of the printed parts, and lack of current structural design procedures. The objective of the research is to define a structural design approach to apply WAM in construction. Up to now, the conventional design approach for traditional constructions is based on a semi-probabilistic approach to calibrate design values and partial safety factors, considering a constant geometry and linear elastic material. For innovative constructions, as the ones realized with WAM, the current approach is the use of the so-called digital twin and advanced numerical modeling to detail the nonlinear material behavior and consider all geometrical irregularities. The approach proposed in my research is the use of the conventional design approach applied to WAM, which uses the semi-probabilistic approach to calibrate the design values, but accounting for the anisotropic nature of the printed material and considering an effective geometry. The experimental investigation was carried out on WAM-produced stainless steel bars realized by 3 different build angles: at 0 degree, so with the same direction as the vertical gravity axis, at 10 degree, and at 45 degree. The aim is to evaluate the possible influence of the different build angles in the mechanical response. The first part of the experiments was devoted to characterize the geometry of the printed rods from 3D scan acquisition. The geometrical irregularities were assessed in terms of lack of straightness and diameter variability. Overall, the distribution of diameter revealed that specimens printed at 0 degree build angle have lower mean diameter of around 5.80 mm with respect to the nominal 6 mm value set for all bars, but higher variability, as those printed at 45 degrees, that have a mean diameter of 6.05 mm but lower variability. For the lack of straightness, a visible detrimental effect of the higher build angle is visible for both mean and maximum value of eccentricity, which could potentially alter the mechanical response of the boss printed at 45 degrees. The mechanical properties were derived through tensile tests on as-built specimens printed at 3 different build angles: at 0 degree, at 10 degrees, and at 45 degrees. The results revealed a non-negligible influence of the printing inclination with a detrimental effect, especially for the specimens printed at 45 degrees. In comparison with the results of the continuously printed specimens cut along T directions, so the transversal, which is perpendicular to the deposition layer, the Young modulus values are on average the same, while the 0.2 stress, which is the yielding stress, is quite reduced for all inclinations. The ultimate tensile strength is severely reduced for 45 the degrees inclination. And overall, there is a lower strength ratio, which is the ratio between the 0.2 proof stress and the ultimate tensile strength with respect to the continuous printing, suggesting higher hardening phase for the dot-by-dot printing. Further studies were also carried out to define the flexural stiffness of one bars through three-point bending test. The resulting stiffness considered the contribution of both the elastic modulus and the real moment of inertia coming from the irregular geometry. From these tests, a correction factor was calibrated as the ratio between the nominal and the real flexural stiffness. The correction factor was also adopted to interpret the first results from compression tests on one bars, tested at different values of length, hence slenderness. Further studies will start from these tests in order to quantify buckling curves and predict the behavior under compression of one bars. In a nutshell, the work presents the first experimental and analytical investigations of one bars for construction applications. Geometrical and mechanical characterization was carried out on stainless steel bars produced with dot-by-dot printing technology and printed at different build angles. The future perspective on 3D printing in construction could see the use of mobile 3D printing solutions able to move on the structures while 3D printing on it. And this possibility could open unexplored construction scenarios also in non-human environments. Thank you for the attention.